So I stopped my last session asking you to think about the probable solution that you could build to overcome the complexity and not to use the linear model. So we have now the solution with us for classifying our handwritten digits data set. So I was talking to build a nonlinear model. So that's the solution. So what is a nonlinear model? Wherein you bring in some non-linearity. When you had your linear model, you are supposed to build a model in which the output is always proportionate to your input that you are providing. Probably directly proportional or indirectly proportional, we are not bothered, but proportionate. You know, when you are increasing the input, the output is supposed to increase or decrease with that measure. But ad hocly it cannot do that. So that is the reason in the real time scenario, it is very difficult to implement and work with such a basic linear model. So that's why you are supposed to bring in non-linearity into your model. So that was the solution I was talking on. So since a linear model is not feasible, we can embed a non-linear function in the linear model and convert it to a non-linear model. So this is the beauty of deep learning here, wherein you can build a non-linear model just by inserting a suitable function into a linear model. So entirely it will be a normal linear model that you will be working. You add up a non-linearity to it so that it can work up to the complexities that have been involved with the increase in the data sets. So we call this nonlinear function here as an activation function. So from now onwards, you will be hearing the name of this function very frequently. So I am talking here about activation function. So from now onwards, when somebody asks you what is an activation function, it is a mathematical function that is added to a linear function to bring in the non-linearity that is required by a deep learning model. So very important element of a deep learning model is an activation function. So if I really want to represent it, I generally prefer to use a sigma for representing an activation function. So you all know that what are you doing? You have weights associated with inputs wherein you multiply both the weights and the inputs and then you add up to the bias. Okay, that's a linear model, right? Y is equal to mx plus c. This mx plus c is a linear model. To that, you are passing it through an activation function which is here sigma. Once you attach that sigma or a mathematical function to that linear model, all you can get is an output and the entire model itself became non-linear in nature. So that's the beauty of activation function, that it imparts to our deep learning model. So now, if I talk on some common activation functions, there is a sigmoid function, you have tan h function, you have ReLU function. More about this you will study as and when I go deeper into the topics, but for now you can say there are three popular activation functions: ReLU, tan h and sigmoid. Now these are all mathematical functions. Okay, so if I talk on sigmoid, then this is how a sigmoid function looks like. Okay, so how do I define a sigmoid function? A sigmoid function, if I am defining a mathematical function, then f of x will be equal to plus 1 for all the values of x greater than 0, and it will be minus 1 for all the values of x which is less than 0. So when you plot it, you get it in this way. Okay, so this is a sigmoid function. Alright. Now, similarly a tan h function will be varying from minus 1 to 1. Now, you have ReLU function, which is one of the very popular activation function. So, ReLU stands for rectified linear unit. So, why it is called rectified? Because you can see here for the negative values, ReLU is giving you a 0 value, and it is like a ramp function here overall towards the positive side. So it increases. So f of x, I can say it is equal to same as x for all the values of x greater than 0, and it is 0 for all the values of x which is less than 0. So that's how is a ReLU function, and ReLU is one of the most important activation functions. So the ReLU function only retains positive part of a function. So that's how I am calling here. There I wrote You can see I wrote f of x is equal to x. Now this f of x is nothing but your output, which I am writing here as y. So what is happening here, look at the beauty, you are having the input, you are applying a non-linearity, which is your activation function, and that is going to give you a output. So basically these are all mathematical models. So y is equal to x is going to be the output of ReLU, but only the positive sides. It will set the negative side to be 0. So it has got a unilateral suppression characteristic because it is going to be increased only in one direction, and in the other direction it is going to suppress it. So single direction suppression characteristic, and although it is simple, but it is a very excellent nonlinear characteristic function. The most important advantage of ReLU is that you can very easily calculate the gradient of a ReLU function, and under the process of training, ReLU is very stable mathematical function. So that is why it is one of the most widely used activation functions for all the deep learning models. Now as we go apart further, we will also see how to decide an activation function for what type of model. But for now, we are thinking that for classification, let us rely on ReLU because it is most basic and most frequently used. But again, I am telling you, as I move forward towards the course, I will let you know how to decide what activation function you are going to use for what type of application. That much clarity I am going to give you once I go through the further topics. So now we convert this particular model that we have been discussing into a nonlinear model now by embedding a ReLU function. So I get an output when you take the inputs, multiply it with their weights, add up the bias, and then you pass them through a ReLU activation function, thus creating a nonlinear model. Now linearity problem is solved. One of the problem is solved that we have been discussing. Now second problem, what was the problem? Complexity. How do I bring in complexity to my model? How do I bring in that much good interconnections between my neurons, wherein I can very quickly get my result even for a complicated data set. So now as the data set is increasing, as the inputs that you are training with are becoming complex, you require a complex model. So how am I going to deal with it? What is the second solution? So the second solution is you have to increase or build your model complexity. So how do I do that? I will try to embed a network. Okay, I would try to now create a neural network rather than a single layer network. We are going to build a neural network with multiple layers. Okay, so we'll see it how do we do that. So to increase the model complexity, we are going to repeatedly stack multiple transformations. For an example, the first layer you are going to take some weights, bias, and suitable inputs. Okay, so this is how it is. You take X, which is your set of inputs, which all of them have a vector of weights for them, and then you give this inputs to your model, wherein you are also giving some biases, okay, and then finally you are getting output. So think like this as a black box. Now something is happening inside it. What is happening? So I just break it down several times and I say that I have this one layer which is taking my inputs. So I am having W1x plus B1, and I am adding a nonlinearity to this layer by choosing my activation to be ReLU. I get an intermediate output which I am calling it as H1. Now this intermediate output will go to the second layer of which is present, which I have divided further. So this intermediate output is now serving as an input to my next layer. So this intermediate output is input to my next layer. It has got its own weight vector, it has got its own bias. Again I implement a nonlinearity, I pass on it to a activation function which is here a ReLU. So to this again I get an intermediate output, the next intermediate output. I am calling this next intermediate output as H2. Now this H2 should go and get me the output if I am stopping. It is up to me how many layers I want to build. Suppose here I am giving 2 intermediate layers. So I just want to now take output from it. So I take this in second intermediate output as an input to my output layer. I have its associated weights and biases, and then I quickly tell Now I know I don't need anything, I just need my output. So this is how you stack multiple transformations and build a network. So you will see in the preceding equations that we discussed, the output value H1 of first layer neuron is serving as an input to the second layer of neuron. It will take the output H2 of second layer of neuron as the input of third layer of neuron, and then finally the last layer is going to be output, and it is the output of your model. So this is what we are trying to do. So what are we trying to build? We are trying to build a complex network. So you can see how the network, a neural network, is actually built. This is the resultant network. So you have got set of inputs, which is your input layer, your intermediate outputs wherein you build it through adding nonlinearity, which is your activation functions. So you got your hidden layer 1, hidden layer 2. You can have n number of hidden layers as per the type of the data you are dealing with. Okay, it is user's choice how many hidden layers you are giving it, but don't give so many hidden layers that you will overfit your model. Give it ample so that it can give you the best optimum solution. Then finally you have got an output layer so far. So this is how a neural network is built. So we call the layer where the input node X is located as input layer. The output of each nonlinear module H1, H2 that I have been discussing with its parameter W and B, it is called a network layer. Or the intermediate layer, in the middle of the network, what are all layers of networks that you were seeing, they are actually called as hidden layers, and the output layer is the last layer that is present. So you can quickly see here, this is the input layer, these are all hidden layers. You always have their associated weights, you have their biases which are coming in, which helps you to calculate further with every layer that is coming, and finally you have got an output layer. So this network structure, which is formed by the connection of a large number of neurons, is called a neural network. The number of nodes in each layer and the number of the layers are going to determine the complexity of neural network. So how many nodes, how many neurons are you using to build this network, and how many number of layers you are using. See, input layer, output layer, by default it is, but how many hidden layers you are using it, based on that is your complexity of the network. So this was about how do you build a neural network. So now we got solution to the problems that we were facing, wherein why you couldn't use a gradient descent, and based on the data set that you have selected, why you couldn't use a linear model, and how do you build a more complex model.